everyone, and welcome to the New York State Schools and Energy Efficiency and PCB Training webinar. Our first presentation will be reviewing Energy Star tools and the approach towards energy efficiency and why you should consider upgrading your lighting. Our second speaker, Mark Mandoloni, will be talking about the dangers of PCBs to human health in schools. Our third speaker, Benjamin Fox from NYSERDA, is the liaison for incentives targeted to K-12 schools in New York State. All questions and answer periods will be answered at the end of the webinar, so please type your questions throughout the presentations, and questions will be answered again at the end of the webinar. I'll start off by giving a brief overview of the U.S. Environmental Protection Agency's Energy Star program for schools and how the program and tools can help your schools. First, Energy Star is a voluntary program. It is a strategic approach to energy management by promoting energy-efficient products and practices. Help schools and organizations save money, and most Americans recognize our logo, especially through the appliance program, and helps promote the demand for energy efficiency. And what do we mean by a strategic approach in energy management? Over the past decade, Energy Star has observed that leading organizations are implementing a number of best practices in designing and implementing their energy management programs. In fact, EPA has been able to distill the common elements of this successful practice to create a set guidelines to help other organizations kickstart their energy management efforts. The Energy Star guidelines for strategic energy management are shown here, and much more information is available online at our website. In short, however, these guidelines act as a roadmap to help organizations assess energy performance, set reduction goals, track energy savings over time, and recognize and reward improvements. The first step is making a top-level commitment to a continuous improvement of energy performance, and a great way to do this is to join Energy Star as a partner. But today we're focused on a critical step to assess performance. Key tools and resources for schools from Energy Star. First, we have Portfolio Manager, a no-cost online tool for measuring and tracking the energy performance for buildings such as schools. Second, there is Energy Star Buildings Upgrade Manual, which is a comprehensive manual covering benchmarking, investment analysis, financing options, retro-commissioning, lighting, air distribution systems, heating and cooling, and best of all, a specific section on K-12 schools. Third, there is a cash flow opportunity calculator that helps decision makers on how much new energy efficient equipment can be purchased from the anticipated savings. Should this equipment be purchased, be financed now, or wait for cash from future budget? Is the money being lost by waiting for lower interest rates? Next, we offer free online training to help improve energy performance to your organization. No travel, no lost time out of the office, no cost, and EPA makes it easy to get the information you need today at EnergyStar.gov/training. We also offer a directory to the Energy Star services and product and providers that have demonstrated their expertise and achievements by meeting strict Energy Star program requirements for benchmarking customer buildings using Portfolio Manager and gaining Energy Star certification for buildings at EnergyStar.gov/SPP. And finally, we recognize top performance in energy efficiency by having schools become Energy Star certified. Let's start out by benchmarking, because it is important to first measure energy consumption, and it offers other advantages, and you can't manage what you don't measure. EPA's Energy Performance Score for buildings also allows schools to benchmark their buildings' energy performance and compare one building against a national sample of similar buildings. Compare all your school buildings of similar types to each other and set priorities of limited staff and/or investment capital. Portfolio Manager is a no-cost online tool for measuring and tracking energy performance of facilities. The tool allows you to benchmark the energy use of all your buildings. Once your data is entered into Portfolio Manager, all the buildings will receive an energy use intensity. It has an easy-to-understand 1 to 100 score that is normalized for weather, operating hours, occupant density, and plug load. For eligible buildings, the energy performance will tell you that your school measures up compared to the national average of similar space types. Receiving a score of 50 means that you are at the national average, while a score of 75 or better makes you eligible for the Energy Star certification. In addition, Portfolio Manager helps you track the energy use of water over time in a single building, group of buildings, or entire portfolios. The tool also allows you to track cost savings, the CO2 emissions, and other types of data. And finally, if any of your buildings are eligible for an Energy Star certification, Portfolio Manager is the tool you use for the application process. Once you have benchmarked and received a score, you'll be able to create an energy plan. A score of 1 through 50, you should really consider a comprehensive investment where the opportunities are the greatest in saving money throughout the whole building, such as lighting upgrades, air distribution systems, heating, cooling, and weatherization to optimize energy efficiency. A score 50 to 74, you should consider a high return investment such as lighting improvements that will yield savings and consider working towards the Energy Star certification. A score 75 to 100, you should definitely apply for the Energy Star certification and always consider getting a higher score because there is always room for improvement. What data is required in order to benchmark a school? Before you can even use the tool, you'll need to gather some data and have it on hand. First and foremost, you'll need the address of the building, and the zip code is definitely an important piece of information, as Portfolio Manager uses zip code to create a weather profile. The energy consumption data is collected by gathering the most recent 12 consecutive months of utility bills. You'll need data from all major sources of energy that you use in your building, such as electricity, gas, oil, and steam, etc., for the same 12 months. And finally, the space type. You'll need to collect it as specific type of building you're benchmarking. For K-12 schools, some of the information you'll need is square footage, the number of months of operation, the number of personal computers, and as well as other data listed here. This is a screen you'll see each time you want to log into Portfolio Manager. At the top of the page, you'll see news about any updates to the tool. At the bottom of the page are some helpful links to additional learning material. If you already created an account, enter your username and password. If not, click Register link below in the login area and create a new account. It's easy and it's secure. All the data entered is not shared with anyone unless you wish to share it with a specific user. Here is an example of a building with all the required data entered. If eligible, the Energy Star score can be seen in the upper right-hand corner. In this case, the test building scored an 88. A score 75 or higher is required to earn the Energy Star. The use of the Energy User Summary View and Facility Performance section and the Energy Use Intensity can be seen for all buildings in your portfolio. Other performance views such as environmental, financial, which is very important for many schools, and the summary of energy use. You can customize the view shown here with over 70 columns of data by clicking Create a View. Document and communicate improvements through the Energy Star statement Energy Performance. This is an unbiased report that is easy to see and understand. In the report, you will see and verify all the data you entered. The report created will be in a nice PDF format that can be printed and shared with your staff. Here are a few statistics specific to the K-12 sector. The nation's K-12 school districts spend more than $8 billion annually on energy, and the breakdown on energy use in K-12 schools. Building systems in a typical school, energy distribution can be attributed to 5 main categories, and this varies by climate zone: lighting, space heating, space cooling, and all other systems. Lighting is a major component, and the staged approach to building upgrades accounts for the interactions among all other energy flows in the building. Each stage changes that will affect the upgrades performed to subsequent stages, thus studying the overall process for the greatest energy cost savings possible. Lighting upgrades come early in the process, as highlighted here, because lighting affects heating and cooling loads and power quality. By reducing internal heat gain, efficient lighting also reduces the building's cooling requirement. Efficient lighting moves the score up in Portfolio Manager. Since lighting can account for up to 35% of the building energy use, the lighting efficiency upgrade can reduce lighting energy up to 50%. The lighting efficiency upgrade can cut the total energy consumption by up to 17% and increase the score up to the same amount. Lighting efficiency is typically considered an energy efficiency low-hanging fruit. Strategies such as switching off lights, delamping, cleaning, and daylighting are simple and inexpensive. Relamping or periodically replacing groups of lamps requires a slightly more investment. Similarly, schools can install dimmers, timers, and sensors to have more control over when lights are turned on. Not only is lighting operations and maintenance necessary for good visibility and security, it also saves money. Simply delamping can save 25 to 50% of lighting energy, which equals to 1/3 of the school's energy use. Teaching staff and students about energy conservation and how to use it in the classroom lighting controls is also a good idea. What is wrong with T12 lighting? First, T12s are an old and inefficient technology. It is an energy hog, Replacing it with T8 fluorescent systems can save up to 40% in lighting energy costs. It is expensive to run. Upgrading to a T8 system usually pays itself in less than 3 years. Upgrading reduces the maintenance costs and concerns too. It generates lots of heat and adds to air conditioning costs. T12 lights flicker, buzz, take a while to start up, or degrade quickly. And upgrading improves lighting quality, uniformity, light output, color appearance, and better lighting can increase school productivity. T8 lamp improvements. Their lamps are small in diameter, increased lamp ballast, system efficiencies, longer lamp life, better color rendering index, and reduced mercury. And finally, the lighting technology means that you don't have to compromise on lighting quality to be energy efficient. The case for upgrading T12s to T8. This table is a performance comparison of fluorescent retrofit options. Packages of lighting efficiency measure such high-performance lamps and ballasts. Delamping controls achieve deep savings with attractive economics. In each case, it is assumed that the minimum illumination of 25-foot candles is maintained and that lamps are replaced at burnout. The power per fixture wattage is decreased in each of cases for the T8 lamps from 156 watts in the T12s, and the T8s go from 116 watts to 45 watts. The annual energy use in kilowatts is also shown to decrease significantly. The energy savings increase, the cost of operations of the lamps definitely decrease in annual operating costs, and the only one-time cost is the upgrade cost. In each case, the cost depends on the amount of technology, such as high-performance lamps, specular reflector lenses, occupancy sensors, and daylight dimming technology. And the payback is from 3 to 5 years, and the school gets to keep the savings after that. The phase-out of T12s. Why are T12 systems being phased out? T12 lamps and magnetic balances are considered outdated technology compared to today's T8s and T5s fluorescent technology, which are far more energy efficient. The phase-out is to remove less efficient T12 fluorescent systems from the marketplace and encourage commercial and industrial facilities to switch to more energy-efficient technologies. You can expect the cost of the remaining T12 products in the marketplace to increase in the near term as replacement supplies dwindles and the lighting manufacturers turn their attention to producing more energy-efficient products such as high-performance T8 and T5 systems. Switching from T12 to T8 light requires a ballast upgrade, and ballast is a device intended to limit the amount of current into the electric circuit to light up a fluorescent lamp. And the magnetic ballasts, or the T12 magnetic ballasts, are older technology with the coarse steel plates wrapped in copper windings. In the pre-1979 ban on PCBs, these ballasts incorporated a small capacitor that contained PCBs. Some of these ballasts may leak PCBs and continue to operate and may be prone to overheat and spark a fire. An electronic ballast is considered more energy efficient than a magnetic ballast. T8 lamps use electronic ballasts to operate effectively, and these ballasts used in new and retrofit projects, and these ballasts are also smaller and run much cooler. Schools that are built prior to 1979 might have lighting with ballasts containing PCBs. This is what you might normally see when looking up at a light. Unfortunately, this PCB-containing ballast had evidence of leaking, but the light was still working. It was determined that the widespread leaking PCB-containing light ballasts were contributed to elevated air levels of PCBs. We have a whole presentation next on the negative effects of PCBs on human health. PCBs are found in these old ballasts in the small capacitor, and the amount ranges from 1 ounce to 1.5 ounces. The tar-like substance of the polymaterial is used to surround the components to muffle the noise of the ballast. Thermocoil switches were commonplace in the mid-1980s, but EPA found thermocoil switches in some ballasts that were manufactured in the early 70s. These ballasts appear to have less leaking since they do not get as hot, but unfortunately, if they're not leaking and get hot, they shut down and cool down and reset and continue to work after leaking and continue leaking. How to go about to safely handle the removal of these lamps or ballasts? First, we need an experienced contractor or staff that should be the only ones working on the potential PCB light fixtures. Follow standard operating procedures for working around electrical fixtures as required. Follow all requirements and precautions if there is an asbestos issue. Move the desk and equipment from underneath the fixture and place plastic sheeting under the work area. Proper storage and disposal. We have seen that in some instances, these old ballasts have just been disconnected and left in the light fixture. We ask that old ballasts be removed from the light fixture and do a complete job. Disconnect and remove all ballasts, incidentals of PCB-contaminated items, and fluorescent tubes from the lighting fixture, housing, and compartments, and provide appropriate containers and packaging material from packaging and storing the 4 possible types of waste streams. Maintain a record for each space where lighting fixtures are removed. Include how many leaking versus non-leaking PCB ballasts were removed from each space. Package and label drums according to federal and state local regulations. Store the drums until the transporter currently licensed for transportation of PCB waste removes them to the appropriate disposal facility. Ballasts that are totally enclosed and not leaking can currently be disposed in solid waste landfills. However, most landfills will not accept such waste, so most will be disposed in a TSCA-approved landfill or destroyed using chemical or thermal destruction methods. For further guidance, please visit the link below. An example of a light action plan done once. So establish a voluntary teacher-student program to turn off lights to save energy. Install building automation systems to monitor motion sensors where appropriate, especially in occasionally used-based areas. Install dimming ballasts if appropriate and compatible with lighting systems. And install an LED lights in exit and emergency signs. A lighting action plan that should be done daily. Turn off all lights in unoccupied rooms. Work with teachers, students, and other building occupants to make this through the lighting patrols or other programs. Turn off all lights at night, with the exception of security lights and exit signs, as safety considerations allow. Turn outdoor lighting selectively, as safety considerations allow, and delay turning lights in the morning until the staff arrives. In the lighting plan that should be done monthly, check that all interior and selected exterior lights are turned off during nights. Analyze lighting building automation systems for opportunities to decrease lighting electricity use, and check broken lamps and replace them. And here are some low-cost measures at energy efficiency opportunities. First, measure and track energy performance. Set back thermostats in the evening and other times when the building is unoccupied. Perform monthly maintenance of heating and cooling equipment to guarantee efficient operation throughout the year. Educate students and staff about their behaviors and that affect energy use. And some cost-effective investments. Upgrade and maintain heating and cooling equipment. Use performance contract to guarantee energy savings from upgrades. Work with energy service providers to help manage and improve energy performance. Purchase energy-efficient products like Energy Star qualified products, and install window films and add insulation or reflective roof coating to reduce energy consumption. So if you have any questions or comments about the information presented, please contact me, and my information is on this slide. You can also find more information about Energy Star by visiting EnergyStar.gov. And thank you for your time and interest in improving energy performance in schools through the help of Energy Star. And we'll move on to our next presentation.
Good morning, everyone. This is Mark Mataloni. I'm a toxicologist at EPA's Region 2 office. I'm going to use a case study of a public elementary school in New York City to illustrate the points in my presentation. But before I get into the case study, I just want to start with one slide that illustrates why we're dealing with this problem in the first place. PCBs were used extensively, starting commercially in roughly around 1930 until they were banned in 1978, and with extremely high use in the 1950s and 60s. Two particular uses of the laundry list you see here that really impact schools were, as Juan mentioned, they were used in these old T-12 lighting fixtures as the part of the ballast capacitors, and they were used extensively as what's called plasticizers. They improved the how should I say they made more pliable the caulk and window glazing that were used to seal windows and door frames, and so they made the products better. They unfortunately added a lot of hazard, and so both of those uses have turned out to be problematic in the schools. Let me go over to our case study. It's a public elementary school in New York City, and the events leading up to why we actually have to do this environmental assessment of PCBs. So PS 199 is a elementary school. It's K through 6. It was built in that prime time when PCBs were being extensively used in 1963. Pretty large, 880 students. It's located on the Upper West Side of Manhattan. And briefly, how it got on the radar screen, a Harvard researcher back in 2004 did a study of 24 buildings in the Boston area where he just took samples of exterior caulk and found more than half of the buildings had PCBs at greater than 50 parts per million, which is just a regulatory limit for the amount of PCBs that could be in non-permitted uses. And you could see actually that the levels were quite high. The mean was over 15,000. This caught the attention in 2005 of a concerned parent in a New York City suburban school where window replacement was being done, and samples taken there also showed extremely elevated levels of the PCBs in caulk, and that was publicized through various media outlets and eventually caught the attention of some of the PTA members in PS 199, where they themselves obtained caulk samples and found very high PCB levels, some over 100,000 parts per million. One of the things that is worth stressing here, and the reason I gave this history is because this initially is what I would describe as a caulk-centric issue. This is where we originally found the problem, was in this caulking and sealant material. Now, you have schools with PCBs. Everyone knows that PCBs are not good things, and they, in fact, have numerous and varied health effects. I'm not going to spend all day. I'm sorry, we're just doing a little repair on my screen here. You just close that right there on the X.
No.
Oh, yeah, just. I'm not going to spend all day on the health effects, but let me just briefly summarize the major ones. There's strong evidence, specifically in animal models, that PCBs are carcinogens. They clearly cause liver tumors. The evidence in humans is somewhat more equivocal, but based on the animal data, EPA designates PCBs as what we call probable human carcinogens, and we regulate them as such. They cause a spectrum of what we would describe as cognitive developmental effects, neurobehavioral, things like impaired spatial discrimination, impaired learning, decreased IQ, altered what we call motor function, which is reduced muscle tone and reflexes, a lot of endocrine type of effects on reduced thyroid hormone, possible adrenal and reproductive effects. Very well-known what we call immunosuppressive effects from PCBs, decreased circulating antibodies in the body, decreased thymus size, which help produce some of the T cells that are in fact used to combat viruses, the killer T cells in particular. And collectively, all these suppressions lead to a decreased resistance to infection, which is really the bottom line here, and that's considerable concern. Other effects, at very high doses, you see this very classic dermatological condition called chloracne, and dioxins produce that. And again, because of their reactivity in the body, they cause a number of liver effects where they're metabolized. Now, so we have the situation where we have PCBs in the school. We know they cause all sorts of effects, as I've just alluded to. The next thing is, well, at what level are these effects caused? And I guess this question was probably posed or addressed best by Paracelsus, which was a 16th century Swiss physician who said the dose makes the poison. So at what level of exposure to PCBs do we have to be concerned with this laundry list of health effects that are obviously quite consequential? On this next screen here, I know it's a little busy, but you see these are actually sampling data rounds from going back to August 2008 through 2010. We have more recent ones, but this is just here for illustrative purposes, where you could see the levels that were found throughout various classrooms and the cafeteria, the gym, throughout the building. And so you look at these numbers and say, well, what do they mean? Well, the first context you could put them in is right up on the top. Our Agency for Toxic Substances and Disease Registry has a document, and they describe urban ambient air background. So if you were to go outside PS 199 and take an air sample, what would you expect to find? And it would be quite low, usually in the area of less than 1 to 10 nanograms per cubic meter. And you can see that the levels here are what we would describe as many orders of magnitude, more than 10 times greater, sometimes more than 100 times greater than the background. So the question then is this, does this cause a health concern? And that's sort of where I come in, because I do risk assessments. And when I gave this presentation to New Jersey, some of the feedback I got was, well, the discussion of risk assessment is perhaps a little too technical for this audience. So I am going to scale it back a little at the risk of being superficial, but I will be here for the entirety, and anyone that has specific questions on any of my presentations, and specifically risk assessment issues, you'll certainly have an opportunity to address them. But very, very quickly, risk is a function of how much exposure you get and the inherent toxicity of a compound. So when we did the risk assessment for 199, we looked at just the kind of what we call receptor populations, so students, teachers, custodial workers, and the exposure. And actually the exposure is very easy to identify and document, because we know just how long, the duration of the time the kids are in that school, from K through 6, how many days a year they're there, how many hours per day, and whatnot. So it was very easy doing the exposure assessment, and because we were finding this in the air, we have very good data on how much air is being exchanged per unit time for the age groups. So we were able to get a good estimate of exposure. The last thing on this slide is dietary background. It's also important to know, well, PCBs are not only coming from the school, but the other major source of PCBs in all of our environment is through the diet. So we took into account what the dietary contribution was to determine how much, to determine an acceptable level in air. And so we have the exposure. The next part of it is the toxicity, and that gets even a little bit more complicated. And I'll just say that, as I alluded to earlier, that PCBs cause both cancer and non-cancer effects, and we need toxicity criteria for both. So on the non-cancer side, we use what we call a reference dose, which simply stated is an estimate of a chronic daily dose with an adequate margin of safety. And that's, I think, the operative phrase here, that is expected to be without appreciable risk of an adverse health effect. And you see this number with lots of zeros on it. That's for one of the commercially available PCB products, for the Arachlor 1254, which was used extensively. And so what we're saying is we like to keep the average daily dose underneath that dose, which is 0.00002 milligrams per kilogram per day. And again, when we keep it under there, we believe we'll be protective of the most sensitive adverse effect with an adequate margin of safety. And that most sensitive effect, as I again described earlier, was an immunosuppressive effect. PCBs also cause cancer. On cancer, there is no threshold of effect. Any exposure can cause at least a theoretical, if not sometimes infinitesimal, increase in excess lifetime cancer risk. So we try to manage that at as low a level as possible. And the way we do that is look at the exposure and, again, the inherent cancer potency of the compound, in this case PCBs. And they do have different potencies depending on what type of PCB, because they are a group of related congeners. When you take exposure and toxicity and put them together, we get what we call a risk characterization. And this is just what I'm describing here as a back calculation. In effect, what level of PCBs in air would prevent either non-cancer or cancer health effects. And you can see the lowest level here is the 200 nanograms per cubic meter, and that's to protect from non-cancer health effects. And so since the cancer health related health effects are higher, we protect for the non-cancer effects or being adequately protective of cancer health effects as well. And when I did the assessment for 199, I looked at both upper bound high-end exposures to students as well as central tendencies. So that's why you see two numbers there, 200 and 300. Our Office of Research and Development subsequently provided what's called an EPA, a PCB exposure calculator, and it generates exposure guidelines in there for different age groups. And you can see it starts down in the 1 to 2 year olds and goes all the way up to adults. And if you look at the midpoint, the elementary school, 6 to 12, the 300 number lines up with the 300 number for the central tendency that we did at 199, because those are essentially the same school type population. So a lot of discussion here. I know I'm throwing a lot of numbers around. The bottom line is we feel that we'd like to keep those numbers in schools, at or below 300 nanograms per cubic meter for a typical elementary school, in order to be, again, adequately protective with an adequate margin of safety. And that's not to say that if we had a classroom where the level was above 300, because you saw that from the data I presented earlier, that there were classrooms above 300. That's not to say we expect to see a health effect. What that means is that we are now chipping away, if you will, at the margin of safety that we as Americans are afforded by our environmental regulations. So that's what we are trying to prevent, is any compromising of the otherwise stringent environmental regulations that, again, that we enjoy as citizens. So because we had this situation, at least in this one school, where we had air concentrations above a level of concern at times, Region 2 entered into a consent agreement and final order, it's called a KFO, back in January of 2010 with the New York City Department of Education, quote, to identify, prioritize, and to respond to the presence of PCBs in buildings housing public schools in New York City. And the way that played out was we started with a program that's just a limited, excuse me, looking for the word, a pilot program of schools. We started with 5, 1 in each of the boroughs. You just see 3 here because the last 2 schools, 1 in Queens and 1 in Staten Island, were done a little later, and we don't have all the data processed for those. But you see what we did in these first 3 schools, including 199, and then 1 in Brooklyn, 309, and 1 in the Bronx, where we did various types of treatment on the cork. And again, this was done because cork was thought to be, at least initially, the primary concern in the schools. And you can see that they did have, at best, a minor effect at reducing the air levels of PCBs in the schools when various types of either cork removal, encapsulation, or some sort of a hybrid where you removed some and patched others occurred. It was at a point along the process that we really came to appreciate how significant the issue of the failing ballast in these older light fixtures would be. And here's just a picture. Juan showed other ones. This is, when you pull down the fixture, you can see this is evidence of a capacitor that failed and either is or was leaking PCBs. So we appreciate that we had another significant source of PCBs in the school in addition to the cork, and we needed to take actions to investigate those sources as well. And you see in this next slide the actual ballast survey from PS 199, where every fixture was evaluated. And you just going down to the bottom, you look at totals. There was a total of 487 fixtures, and almost 75, around 75%, 373 of them were PCB containing. And then if you look over towards your right, out of those 373 that contain PCBs, the vast majority, 334, either were actively leaking or had some history of leakage. And so it's no surprise that we have had the problems we've had in this school with elevated indoor air levels of PCBs. My last slide will just indicate in these box charts that what we have been doing in the New York City schools is various actions taken to reduce the levels, and you could see, well, the the grouping on the left is for all three schools combined, but let's look at the individual schools. PS 178, actually that school never had that many fluorescent PCB-containing fixtures in the first place, so their levels were never that high right from the get-go. But in 199 and 309, you see a similar pattern where the initial levels were quite high. After they took the cork out or did some remediation to the cork, they came down, not quite to the levels where we would be satisfied. Again, we're looking at numbers of 300, and you can see the averages are still above that. And then there was some ventilation done, and of course ventilation helps, and that's part of your toolbox for reducing PCB levels and actually for reducing any other airborne hazard. So I don't want to underemphasize the importance of good ventilation in the schools, but we really got the next significant reduction in PCB levels in the indoor air after the fixtures were removed. So if one wasn't persuasive enough in selling this as a cost-efficient initiative, let me just say that it's also very important is if you have these PCB containing all the ballasts, and it's a big step forward towards reducing the PCB hazard. May not be the only one, and if you have one of those schools that dates back to the 50s and 60s, you may still need to be looking at cork and some other PCB containing materials. But we know there's a straightforward, not cheap, but a straightforward and ultimately cost beneficial fix for the PCB containing ballast. So at that, I will pass it along to the next speaker.
Thank you, Mark. And just a quick reminder that these PowerPoint slides will be available, and there will be a transcript for the presentation. Some people have asked that. So I'm going to go to the next presentation from NYSERDA. Just give me one moment. Ben? Ben? Benjamin Fox? Hello, Ben? One moment, people. 1 second.
Hello?
Ben?
Can you hear me?
Yes, now we can hear you. Your slides are up, Ben.
Okay, perfect. Thank you very much. Good morning. As I said, my name is Ben Fox. I'm an Associate Project Manager with NYSERDA. I wanted to thank EPA for allowing us to join you today, as well as thank you to all the participants for taking time out of your busy days to join in on this informative webinar. Today I will be presenting to you Lighting Your Way to Energy Retrofits, a brief overview of lighting and lighting technologies. Next slide, please. So what I will be covering today is a brief introduction of myself as well as NYSERDA, a brief overview of NYSERDA, lighting basics, lighting technologies, lighting audits and calculations. We do have some time at the end for a couple case studies, and then a conclusion and questions and answers. Next slide. For anybody that's not familiar with NYSERDA, you may be asking, what exactly is NYSERDA? Well, NYSERDA is the New York State Energy Research and Development Authority. It's a public benefit corporation established by the New York State Legislature in 1975, and NYSERDA is tasked to address the state's energy and environmental challenges. It's the mission of NYSERDA to use innovation and technology to solve some of New York's most difficult energy and environmental problems in ways that improve the state's economy. What does all this mean? Basically, we provide information and resources, audits, and capital incentives for your construction needs. Specifically, also, NYSERDA provides free benchmarking to all schools that pay into the system's benefit charge. Next slide. NYSERDA receives its funding from numerous different areas, the most significant being the systems benefit charge and the energy efficiency portfolio standard. Both of these are line items on your utility bill. If you pay into these funds, you are eligible for NYSERDA programs. We also received funding from the Regional Greenhouse Gas Initiative, and as most of the projects are completed at this time, we also received some funding from the American Recovery and Reinvestment Act. Next slide. So I'm going to go over some lighting basics, and I'm going to try to keep this on a very high level and not get into too much detail. But just to understand lighting, you need to know some of the definitions, the technologies, the lamps, the fixtures, and what to look for within your own facility. Next slide. So the lighting basics, you need to understand illumination levels. A lumen is the amount of light generated at the source, directly at the bulb itself. There's a power input, the energy, and then there's light output that's generated by the light itself. There's multiple different levels to lumens. There's the initial lumens, which is right as you first turn it on. The maintained lumens, which are your average lumens over time as the electrons within the light settle down and it becomes constant. And then also lumen depreciation. Just as all other electronics depreciate over time, so do your lamps and light fixtures. Also, foot candle. A foot candle is the amount of light on a task area. It's originally measured as the light given off by one candle at 1 foot, and it's just like any other measurement, feet, inches, yards. It's just a measurement used with lighting. Next slide, please. To continue with foot candles, there are average horizontal recommended maintained foot candles for specific areas and space types. This is a quick example of a couple space types you might find within your school district and the average recommended maintained foot candles. Also to note that the foot candle does drop the further you move away from the light source. Also, the distance from the light source to the area where you're shining that light will also change. So you can see recommended lighting at a desktop is 30 to 50 foot candles, and science labs also 30 to 50, compared to your shop area where you want specific or right around 30 to 75. As your students may be using heavy machinery or equipment, and you want better illumination levels there. Next slide. To continue with the basics, you also have to understand that there's a color temperature, identified as CCT in the technical sense. Color temperatures are measured in the Kelvin scale. And why is it called the color temperature? Well, if iron were heated to various temperatures, it would produce the following appearances. It's arranged from cooler to warmer, where the higher the temperature, the cooler it is, from what appears to be like the northern light or the blue sky we see in the sky to a dull red or a candlelight. Next slide. Just to reiterate, color temperature. The higher the color temperature, the cooler the light looks, the more blue it is. And with the lower temperature, the more red. Off to the right here, you will see the same bulb heated to different temperatures and presenting that color change. Next slide. With color, there's a color temperature, and then there's also color rendering index. The term color rendering describes the ability of an artificial light source to render colors accurately, as rendered by the sunlight. The color rendering index is a rating from 1 to 100 that quantifies the effect that a light source has on colors. You can see in the examples below how color can affect how images appear. It should be noted that when you're lighting within your schools, you really want to go for something with a color rendering index of 80 or better, which gives a better color rendering. Next slide. So there, in addition to all the other basics I've gone over, there's also the metrics. These basic lighting metrics are what's going to help you identify areas for improvement within your schools. There's watts. Watts is the measure of the electrical power as the input. The power coming into the school, which actually produces the light. And the lumens, as I described before, is the light output of the lamp or an entire fixture. The higher the number, the more light is emitted. And with watts, the lower the wattage, the less energy is used. And then there's efficacy, which is lumens divided by watts. And the higher that number is, the more efficacious the product. Also, with current, I'm sorry. So you can see in the right is a lighting fact sheet. Imagine this as a nutrition label on the side of a box. If you walk into your local home improvement store, you might even see these starting to appear on the backs or the sides of light bulbs. And it's with the Department of Energy, this is rolling out more and more. And this will show you the metrics that you need within your school. Next slide. To conclude the lighting basics, you also have to understand the lighting power allowance and lighting power density. Lighting power allowance is the power allowed with the New York State Energy Conservation and Construction Code. That's what is allowed within your space. And then there's the lighting power density. This one is more applicable, as this is what you currently have. It's the total wattage dedicated to lighting divided by the total area. Next slide, please. Now I'll describe some basic lighting technologies. These are some things that you're probably more familiar with. Next slide. The oldest technology, incandescents. These are being phased out now and hopefully aren't being used in your schools at this time. Like I said, it is the oldest lighting technology. It works as the filament is heated by electrical current and it glows. The phase out of the incandescent light is to begin with a 100-watt bulb in 2012, and by the end of 2014, the 40-watt lamp or bulb will also be phased out. Next slide. As Juan spoke about before, we also work with linear fluorescents. There are three main types of linear fluorescent lamps: the T12, the T8, and the T5. This works as an electric arc that excites the mercury atoms, emitting UV radiation. And the UV radiation strikes the phosphor coating within the tube and emits visible light. Depreciation occurs when that radiation, ultraviolet radiation, diminishes the phosphor coating. Next slide. So there's linear fluorescent, and you often hear people say, oh, I have a T5, T8, T12. What, T what exactly? The T represents the lamp shape, tubular, and the number following represents the lamp diameter, in eighths of an inch. The T85 has a diameter of 5/8 inches, and a T5 has miniature bipin bases, while T8 and T12 lamps use medium bipin bases. Also the T5 is nominally shorter in length, and that's why you can't put a T5 and a T8 fixture, or T12 and a T5. Next slide. As we phase out incandescents, we're moving towards the compact fluorescent. There's multiple different types, and as the technology advances with these, the lighting color is actually more appealing to people. There is the twin and quad tube preheating, which ranges from 5 to 28 watts, which has 2 pins with a starter in the base. And these lamps these lamps have a tendency to blink on. There's also the twin quad or hex tube rapid start, which ranges from 5 to 50 watts. It has 4 pins in the base and is nearly instant on. This technology is also dimmable. There's also the more convenient screw-in compact fluorescents ranging from 7 to 38 watts. They're integral and modular, and they preheat and have an electronic ballast built right into the bulb. And some are dimmable. Next slide. You may find your school actually uses a lot of these. These are high-intensity discharge lamps, mercury vapor, metal halide, high-pressure sodium, and low-pressure sodium. Metal halide are commonly used in industrial facilities, sports areas, and they're areas where good color rendition is required. Also, you might find these most specifically within your gymnasium. High-pressure sodium have a higher efficacy than metal halide lamps, but the color isn't quite as good. It produces a light golden color, and it's commonly used for outdoor applications such as your parking lots, your industrial facilities, and for large gymnasiums. And the most efficacious would be the low-pressure sodium, which has the highest efficacy, but however, the poorest color rendition of all lamp types. As seen to the right, it produces a pumpkin orange color. Next slide. And now the new technology that has everybody excited these days is the light-emitting diodes, or LEDs. It should be noted that currently they are much higher cost. However, as it's an emerging technology that's expected to come down and is really coming down on a monthly basis. The market, it really is changing monthly. Good replacements include refrigerator case lights, display case lighting, track or monopoint directional lights, garage canopy, outdoor lighting, and downward lighting. They're really good in the outdoor lighting, as the main down point of them is that they produce a lot of heat. This being New York, it's cold 7 months out of the year, and outdoor lighting actually, that heat, the cold actually helps the fixture work. Some bad replacements are the replacement tubes. The technology isn't quite there yet, and it's just not a good technology at this point. It should be noted that LEDs are the most efficacious across the entire spectrum of light sources, as it ranges everywhere from 0.5 to 1,000 watts. It can be used in all aspects of lighting. Next slide. So here's a quick summary of color temperature and color rendering index by technology. You'll notice that natural daylight has a CRI of 100, and then all the technologies vary from there. As I described before, incandescents are what our eyes are most used to. It was the oldest technology, and that's what we have become accustomed to. Next slide. Also, as a summary, we have some source efficacies. This is identified as the lamp family, the lamp type, and the watts, and the efficacy. You can see incandescents efficacy ranges from 4 to 23, and it ranges from there. The most important thing to point out is the watts and the efficacy of LED, as it is the most efficacious across the entire spectrum of light, and can and will be used moving forward. Next slide. Some fluorescent fixture types that you should be familiar with are listed here. You'll find these throughout your school depending on the lighting need in that area. Downward lighting, usually used around display cases or entryways, and suspended or wall mount in the classrooms or hallways. Also to the right is a high bay fixture. Next slide. Exterior lighting also has its own type of fixtures and varies. You have your pulse start metal halide, high pressure sodium, LEDs, and specific controls just for those type of fixtures. Next slide. So I've explained some basics for you, what to look for. Now I just wanted to go over a quick do-it-yourself lighting audit that you can do within your own school or facility. You do need to record some information. I've provided a basic table here of just some ways to make it look easier for yourself. You do need to go and just get some of the basic room information, your length, your width, your height. That'll help you identify what type of fixtures and what type of lamps to be using. I also need to note that both NYSERDA and the EPA does have tools on our website to help you with this. And if you have any questions or need any help, feel free to contact either of us. What you really need to start off with is identifying your baseline. Your baseline is total watts. I'm sorry. Baseline is what's currently in your school. You need to identify your existing fixtures, the quantity, the lamps in the fixture, and the fixture wattage. Once you have that, you can multiply your number of fixtures by your watts per fixture, and that'll provide your total watts. Total watts existing less your total watts new will be your watts saved. Then you can go either way from there. You can either multiply that by 1,000, and that'll give you your kilowatts saved, and then multiply it by your hours of use, and that'll give you your kilowatt hours saved. Or you can go with the calculation right there. Take your watts saved, multiply by your hours of use, and then divide by 1,000 to give you your kilowatt hours saved. This kilowatt hours saved is how NYSERDA and the utilities in New York State will adopt your incentive to help you pay for your lighting upgrades or your energy efficiency upgrades. Next slide. So now I just wanted to go into a couple of real-world cases, some real projects that we have done through in schools in New York. The first one was done right at Salem Central School District in upstate New York. We retrofitted numerous lamps and also installed some occupancy sensors throughout the entire facility. The total project cost came to about $81,000, just over $81,000. And we provided an incentive of over $11,000. Energy savings were right around 99 kilowatt hours annually, and annual savings of $11,000. The simple payback for this project was just over almost 6 years, 5.89 years. Now to the right, you can actually see the pre-case on top and the post-implementation underneath. They're different hallways, but the same fixtures were throughout. Next slide. Moving into a deeper energy retrofit was at the Brighter Choice Middle School in Albany, New York. We provided over 50 remote-mounted occupancy sensors, over 750 new fluorescent fixtures, T8s, T5s, T5 high output, wall pendants, high bay, and 4-foot troughers. We also installed demand-controlled ventilation, and economizers were added to the new air handling units. This did come through our new construction program and had an incremental cost, or an incremental cost is the cost that was above just building to code, had an incremental cost of $51,000, a NYSERDA incentive of just under half of that. And annual kilowatt-hour savings of over 105,000 kilowatts, with an annual energy savings of $12,000 and a simple payback of 2.2 years for building above code. Next slide. And another deep energy retrofit that came through our new construction program was the Syracuse City School District. We provided variable air volume ventilation systems and variable speed drives for their HVAC, as well as economizers and carbon dioxide sensors. Additionally was the lighting, occupancy sensors, and premium efficiency motors and Energy Star transformers, which help buy down the total cost of the project. And we also provide building commissioning. Again, this came through our new construction program, so they did have to build to code. However, they decided to build above code, and we provided an incentive for that. The incentive NYSERDA provided was over $150,000 with an annual energy savings of over 422,000 kilowatt hours, providing annual savings of over 55,000 kilowatt hours. Also reduced the peak summer demand reduction, which had a significant impact on the utility bills for the school. Simple payback for building above code for this project was just over 1.1 years. Next slide. Some additional lighting resources that you should take into consideration is the Design Lights Consortium listed there, as well as Energy Star and the Consortium for Energy Efficiency. There's also some additional lighting or additional resources underneath there. One you should pay particular close attention to if you do want to get into some more of the technical aspects of lighting is the Lighting Research Center at Rensselaer Polytechnical Institute, listed right there. Next slide. So in conclusion, I explained to you the basics of NYSERDA, the basics of lighting, the definitions, some lighting technologies, how to perform your own lighting audit, and showed you how using NYSERDA or utility incentives can buy down the cost of a project, and that using lighting will, as I said, buy down energy retrofits. Lighting can, because it has such a significant and quick payback, you can bring in some of those measures that have a longer payback to buy down the entire cost of the project. Next slide. So again, I wanted to thank everybody for participating, as well as EPA, TRC Energy Solutions for assisting me with this presentation, as well as ERS. And if you have any additional questions specifically about NYSERDA's programs or incentives specific to New York State, please email us at k12schools@nyserda.org.
Thank you, Ben, very much. And we have a couple questions that we're going to cover. Just let me get out of the slide a moment. We're just going to go back to the slide just to answer a couple questions.
Thank you, Mark Mataloni again. So I have 3 questions here. They're all from the same person. One, Jody Feld. Thank you for your questions, and I'll answer them in the order that we received them. The first question, I assume the PCBs in the cork at PS 199 were in the cork that was being replaced, not in the cork that was used to be put in the new windows. Yes, that's precisely right. The question goes on, can you discuss the exposure route from the PCBs in the cork that would have been a concern? Good question, Jody. There are a number of concerns, and I don't know that we're through with them yet either. We know that, for one thing, when there were PCBs in the cork, they were in quite high concentration, as you saw from some of the data I presented. Some of the samples had over 100,000 parts per million. That's more than 10% PCBs by weight. So even though the cork itself doesn't have a tremendous amount of surface area, right? You're just looking at this bead around windows or doors. It does have high concentration, so we are concerned about the amount of PCBs that could off-gas into the air from that cork. There is a smaller concern about kids that might just touch the cork and around the window or door frames in their normal activities, and either then transfer some some deteriorated cork onto their hands, and then we know kids put their hands in their mouth quite often, so we could have some transfer and some ingestion exposure that way. And then finally, and I didn't talk really about this, but it is a smaller concern that we also know that PCBs can go through the skin. So if you are in direct contact with them, you might not only be ingesting some of the PCB dust from the cork, but you can actually absorb PCBs through the skin as well. So the other major concern, and our Office of Research and Development is diligently working on this right now, is that these PCBs seem to migrate into everything. We know that they migrate into the surrounding material. So if the cork was put next to like a concrete or brick wall, it migrates, especially into something like brick, which is very porous. So then that becomes a secondary contaminated surface, which in itself can then off gas and then also come in direct contact with. So those are the kinds of exposure pathways that are of concern with just the cork. Let me move to the second question, and that gets really back into the weeds of my presentation, and that's fine. You called me on this, so I'm going to get it a little more technical now. And the question is the 0.0002. That would be 0.02 micrograms, or 10 to the minus fifth milligrams per kilogram per day, the reference dose for all exposure routes. And that's a very good question, and it does apply to all exposure routes. This reference dose was based on actually a study in primates where they were administered to PCBs in diet. So even though it was done orally, we understand that it would apply to PCBs that came in through other routes of exposure, and the other two major ones are inhalation, which is really the big concern here into schools, and also what we call percutaneous or transdermal, going through the skin. We do have less robust toxicity data on the effects of PCBs through inhalation route, but based on everything we know about PCBs, that they are absorbed similarly, either through ingestion or through the respiratory tract. They are metabolized pretty much the same way. They don't have what we call portal of entry effects. They don't cause effects directly in the lung or in the stomach, so we're not concerned about the route-specific toxicity. They really cause, we're concerned about a carcinogenic effect and all these other systemic effects that I described. So that reference dose does apply to all routes of exposure. And the flip side of that, and that is why I specifically spent time when I was talking about the exposure assessment, is when we look at the safe level for the indoor air in school, we needed to consider all the exposure routes that are for PCB in someone's environment. And like I said, we may have not gotten every single one, but outside of what is being, what exposure is occurring in the schools, again, I had mentioned the other primary source of exposure in one's environment is through the diet, and that is oral. So we are looking at both the oral exposure and the inhalation exposure when we back calculated out that safe level for PCBs in indoor air. So yes, the value applies to all routes of exposure, and the risk assessment considered all routes of exposure. So I think there's a concordance there. And I see Jody is sending me something. Why were PCB levels higher? Okay, and that's the next question. Why were PCB levels higher in PS 178 after remediation and after remediation for caulk and ventilation. So now let me just ask you to focus on that chart with the box charts that is up. And as I said, the levels started out pretty low in PS 178 to begin with, and they did go up after the caulk remediation. And my colleague who's in the room here with me, Hank Mazuka, pointed out a very important consideration that this was done, during various periods. This study was done mostly in the summer, but the temperature certainly wasn't constant over this time, and we had no real control over that. We had to take the samples when it was available, and the temperature did vary. And I don't have that information right in front of me, but we do have that, and I believe that it was a warmer day after the caulk remediation, and we know that the hotter the temperature in the schools, the more volatilization of the PCBs you're going to get. So that is the most likely reason for what clearly looks like an anomalous result. But one of the other things that we had talked about is that the PS 178 also received that hybrid type of approach where we took some out, we paired other parts, and it could very well be that disturbing all the PCBs in the caulk actually liberated some while we were in the process. Again, we didn't remove it all, so we just took some out and encapsulated others. So it could very well be that there was some mobilization, at least temporarily, which was captured on the next round of sampling. So it is something that you would not expect, and I think those are probably the two most likely answers. Your question did state that the levels went up after remediation of caulk and ventilation. I would challenge the ventilation, because even though that box does go up a little bit more, and if you're not familiar with box charts, let me just give a quick summary. That horizontal line that exists in all of these boxes is the mean level, or the average level. And actually, the average level, if you look at those, did come down. There was just a little bit more variability in the level. So the ventilation did have some impact. It wasn't as great as it was in 199 or 309, but it was a minor impact, and it was more variability. So I hope those were sufficient answers to your questions, Jody, and thank you very much for them, and they were excellent questions.
So we have another question from Joseph with, if all leaking PCB ballasts are replaced, can fixtures be cleaned and reused, or must they be replaced? And here we have a toxicologist who will answer that question.
Good afternoon. This is Vicki Payne. I was one of the inspectors at the New York City schools in January. And if you find a PCB ballast that is leaking, but there is no evidence that that leakage contaminated the fixture, then the ballast can be removed and disposed properly, and you can reuse the fixture. If, however, you find that a leaking ballast has probably contaminated the light fixture, you really should replace the entire light fixture and dispose of the light fixture as contaminated with PCBs. The regulations do allow for decontaminating the fixture. However, the process would probably be cost prohibitive when you take into account that you have to capture all of your materials that you use to decontaminate with and dispose of those as tossable waste. So we recommend that you just replace the entire fixture in that instance.
And we have a couple other questions for NYSERDA. Ben, are you still there?
I am.
Yes, they're curious to know if any municipalities are switching over to LEDs, like for street lights.
That's a very good question. And actually, through the American Recovery and Reinvestment Act, we did help fund some municipalities change over to LED streetlights. One comes to mind is the city of Elmira. I think they did approximately 2/3 of all the street lighting in their municipality that within the city limits changed over to LEDs. the LED street lighting actually provides less light. However, the color rendition is much better and makes it appears to be more visible. You can see the textures in the grass at night. We've also gotten some compliments or comments on how it has increased security and reduced crime in certain areas. But yes, it is available, and NYSERDA does provide incentives for that. You would have to come through our existing facilities program, and it would be on a performance-based level.
Thank you, Ben. One second. And I have a question for the December 12 New Jersey presentations are available. They are available at this website that everybody registered at. You just have to go under the information and go under New Jersey. I'm going there. You can download all these presentations at this website here. I'll send that website again from New Jersey. And New York would have a similar web page on New York here, which doesn't have the presentation right now, but they'll be up by hopefully within 2 days. And the webinar recording will hopefully be there within a couple of weeks. I have a couple more questions coming in.
Okay, we were caucusing among ourselves here. Some of these questions, I think any of us, they're good questions, and they should probably be answered by anyone in the room. So I'll ask Vicki or Hank or Juan to chime in if they want to add to what I'm saying. And the first one comes from, again, this is Mark Mataloni. Cynthia Mitchell, what is being done to address mercury in the fluorescent light fixtures that are inadvertently broken? This whole issue of compact fluorescent bulbs is a considerable one. There is not a trivial amount of mercury in these bulbs, and more than in the old incandescent ones, we probably had no mercury. The EPA has a website, and I think if you just Googled, EPA and compact fluorescent bulbs, just do that, you will find reams and reams of information on how to manage broken compact fluorescent bulbs. And I think that's the best explanation I could give right now, rather than trying to go into a lengthy discourse on actually how to do it. There is a lot of information on EPA's website that addresses every element of the local cleanup and disposal and even commercial disposals of compact fluorescent bulbs. So we have that, and there was the second question on here comes from Peter. Here I am Italian. I can't even pronounce an Italian last name. Puglialessi. I'm butchering that name, but Peter. Anyway, you asked, have you tried ballast-only removal or ballast-first removal to determine if that has a more significant effect?
Yes, great. We just did that this summer.
Okay, Hank, Hank Mazuka is going to speak to that. Let me just say that in our first 3 schools, because as I said, we were Cork-centric, we did those, and so. But I also mentioned that we had 2 schools, PS3 in Staten Island and 1 in Queens, that we were doing later, and I think we learned from those, and Hank will explain exactly what we did learn.
Sure. In PS3 in Staten Island, initially the intent of the pilot study was to have them replace all the windows and the window caulking. When ballast became an issue, a potential issue, the city and EPA agreed that they would do a complete retrofit at that school, which they did last summer. And they took air samples, and they showed a reduction in the amount of PCBs in the air as a result of that complete retrofit of removal of all the old PCB-containing light ballasts and upgrading to newer ballasts. And they've also have gotten a tremendous amount of applause from the teachers and the kids in the school for better lighting, more conducive to education. So that was done. We're probably going to go back and do some additional testing after the windows are done, to see how much of an impact you get from the ballast, from the windows, and I'm sure modifications in the HVAC system, whether they can pump more air through the building, whatever. Those are all things that we're currently looking at right now, because they are, you know, it is a pilot situation in these 5 schools, and we too are still learning as we go along.
This is a question for Ben, and also we can also answer this question with this chart. It says, what is the typical payback period for retrofitting and replacing PCB-containing ballasts? Did you know that PCB-containing ballasts, which are usually T12s, are the most inefficient ballasts and lights out there, lamps? So under the Energy Efficiency Performance Contract with energy service companies, where upfront funding incentives are not provided, is 10 years a good incentive? Well, it's not 10 years. It's usually 3 to 5 years, as you can see in this chart. If you get an incentive, you're going to pay back even quicker. So, and the prices could range, I mean, depending on the technology you use, from a simple case of just an electronic ballast to a really good lighting technology with occupant sensors and daylight dimming. And the cost varies on the, you know, I think here it has the upgrade costs could be vary from $1,000 to $2,000. Of course, this is 2005 prices, but it's similarly, the better technology you use, the more costly it's going to be. Ben, do you want to chime in at this question?
Yeah, just as Juan was saying, you know, it definitely varies depending on the number of lights that you're changing out, number of ballast fixtures, whatever. Also, you know, with the energy performance contract, it is a contract, so there, you know, there's additional costs within there. But it, you know, on average, NYSERDA's existing facilities program, which offers incentives from everything from lighting to HVAC to motors and drives, as well as commercial refrigeration. We have an average 10-year payback on all measures. And that's the way that works is you do the work up front, and then you just submit the cut sheets, and we give you a rebate, if you will, based off of those purchases and installations.
Thank you, Ben. So this is it for the webinar, but there's nothing more questions coming in, so we're going to wrap it up. Thank you for joining, everybody. And again, we'll send you this website. Anybody who registered, I'll send out when the webinar recording comes out. The presentations will be posted. I'll also send that out. And have a great day. Thank you for joining us.